from the heart of Cairo, under the flag of Egypt. A spark was born inside the walls of Ain Shams University.
I'm Abdul Ghaffar and I have the honor of leading ASU ROAR. As a part of ASU racing team, we have always challenged ourselves on the international stages. From Formula Student UK, Shell Eco Marathon, and Formula AI, where we explored the autonomous vehicle technologies. But curiosity doesn't stop. It grows, it evolves. It led us to robotics. That's where we built our ROAR. Behind every great mission, a great team, driven not by years of experience, but by belief, passion, and purpose. We may be young, but together we've built more than just a rover. It's a vision. ROAR is made up of 6 tightly connected teams. The management team, overseeing planning, logistics, budgeting, and public engagement. The robotics team, focused on building our evolving manipulator and end effectors. The mechanical team, developing and validating the rover's structural and mechanical systems. The electrical and low-level control team, powering and connecting all rover's systems through PCB design, embedded control, sensor interfacing, and battery management. The autonomous system team, building the system of the rover by integrating computer vision, sensor fusion, path planning, and control algorithms into a cohesive autonomy stack. Our newly formed science team, conducting field experiments for rock classification, pH analysis, and biosignature detection. The drone team, designing, assembling, and testing drone hardware while developing software for autonomous flight and mission programming.
Each of us brings something different to the team, but we all share one mission: to face new challenges. That's why we found the European Rover Challenge, a competition that pushes us beyond anything we've done before. To us, it's more than just a competition. It's a chance to design a rover that's ready to take on the unexpected and to become one of the first Egyptian and African teams to compete on site. We're not just here to compete, we're here to collaborate, learn from one another, and stand among the best innovators in the world.
Our mechanical system is designed with a focus on adaptability, practicality, and ease of integration. The structure uses a modular layout, letting us reconfigure the rover for each ERC task. The rocker bogie suspension is used for passive terrain adaptation, helping maintain ground contact over rough surfaces without active control. One of our main upgrades this season is our newly designed wheel assembly, focused on structural strength and durability, and is now ready for manufacturing. This year, we've added a new drilling mechanism and storage mechanism to be able to do all the ERC tasks. Altogether, the mechanical system reflects practical design choices and steady development, aimed at reliable operation at the competition.
From switches to rock and sand samples, every precision task relies on a capable, well-engineered robotic manipulator. Our 5 degrees of freedom robotic arm has come a long way since its original design developed last year. This season, we have re-engineered key joints for higher torque and improved stability, integrating cycloidal gears and custom double-stage belt drives with optimized gear ratios. These upgrades reduce backlash and enable smoother motion under load. To meet the varied demands of ERC tasks, we have designed modular end effectors that can be swapped quickly, enabling the arm to handle sampling tools, control panels, and scientific instruments with precision. Most of the components are being designed and manufactured in-house, giving us full control over tolerances, performance, and integration. The cycloidal joint is currently under active design and testing.
Rover uses CAN-based architecture based on STM32 microcontrollers. Each node controls a specific subsystem and communicates over a shared CAN bus. Each subsystem is implemented on a custom-designed board. The boards are equipped with the necessary communication, power management, and control elements based on the subsystem's requirement. The layout was optimized for minimal noise and efficient routing. Our system includes various sensors used for navigation, environment monitoring, and scientific tasks. We made sure each sensor is properly connected and tested under real-world conditions. Calibration was done to ensure reliable measurements, which is crucial for autonomous operations and task accuracy during the competition. Power is supplied by lithium-ion battery packs managed by a smart BMS. Using a Bluetooth app, we monitor cell voltage, temperature, and state of charge in real time. The system ensures safety and logs any faults during operation or charging.
At ASU ROAR, intelligent navigation is key to mission success. Our rover is built to explore unpredictable ERC terrain efficiently, safely, and autonomously. It all starts with the A-Star Global Planner, which maps the most efficient path through required checkpoints, optimizing travel time and avoiding hazards. But ERC terrain is dynamic. That's why our rover perceives its environment in real time. The Z2i stereo camera captures dense 3D point clouds, identifying rocks, slopes, and obstacles. This obstacle identification approach is model-free, relying only on raw data processing. This perceived data then powers our 3D artificial potential fields, which allows the rover to react instantly, navigating around unexpected obstacles without delays. Once a path is selected, our adaptive pure pursuit controller takes over, guiding the rover along its trajectory with precision and stability, even over uneven surfaces. Reliable localization ensures we always know where the rover is. Our unscented Kalman filter fuses sensor data to deliver accurate position estimates, while Aruku marker detection provides absolute updates, which is critical for tight maneuvers and tight alignments.
We're currently working on a heuristic to find the best landing spot, both in terms of safety and scientific value for the scientific exploration task for the ERC. We're also preparing for the AstroBio task by pre-calibrating our pH sensor to ensure it's ready for field use. Our drone is entirely designed, manufactured, and assembled in-house. The current frame is made from ACM, a lightweight composite of polyurethane sandwiched between two aluminum sheets. However, to further reduce weight and improve strength, we're shifting to a new carbon fiber-based body, also made in-house, starting from the layup process to produce a sheet which will then be CNC'd into the desired shapes. The drone is powered by a Pixhawk 2.4.8 flight controller, which is integrated with Mission Planner, which is used for real-time monitoring, reviewing flight logs, and configuring flight parameters. It's connected to a Raspberry Pi, which runs our vision and detection software, and enables wireless communication with the ground control station via UDP using MAP proxy during flight. Our BLDC motors are driven by a 4-in-1 ESC, powered by a 3DR power module. This module not only powers the system, but also allows the Pixhawk to monitor the battery level and trigger an automatic landing failsafe if needed. For navigation and control, the drone uses a TF Luna LiDAR for altitude measurements, an IMU and compass for orientation, and a downward-facing camera for optical flow and Aruku-based pose estimation. The ground control station consists of a laptop running Mission Planner for live telemetry, as well as a FlySky RC controller as a dedicated emergency tool, allowing manual override or forced landing in case of emergency. This ensures robust control and operational safety throughout the flight.
We are developing the robotic manipulator's control system, implementing forward and inverse kinematics both in simulation using MoveIt and in real-world tests, ensuring the manipulator performs reliably across different scenarios like samples pick and place, handling plugs and switches. Our storage system has sample holder, a protective lid to protect the sample while navigating through the Morse yard, and a load cell to measure the sample's weight during collection. The drilling mechanism prototype is now complete and has been tested successfully. It showed stable and consistent motion with effective sand extraction during operation.